Hello.
Huh? Thanks. Appreciate it.
The proofs are really readable, so.
Yeah, I mean, it's a fun little area because, the proofs are, they're kind of like brain teasers, right? And you could just put, each one kind of fits on a slide.
They look sequential too, because
Yeah.
disprove this.
Yes, yes. Even though, the way we realized these things was like completely in a weird, crazy order. But tried to make it more linear.
I can't believe you tried to do something like the day of.
Well, it's just, what happens is when I'm preparing the talk, and I'm like, okay, someone's going to ask me why you couldn't just do this, so I need to have an answer to that. Or, wait a minute, you can do that.
Are you staying for the cryptography one too?
Wait,
Yeah.
no.
All right, welcome back from the lunch break. We are continuing with Dakshita, who will tell us about quantum cryptography from P-hardness. Please take it away.
Thanks. Thanks for having me here. We gave a version of this talk tailored to cryptographers last week. This one is going to be tailored to quantum information theorists and quantum complexity theorists. Please feel free to ask if you have any questions. This is based on 2 joint works with my student Kabir Tomer. We get started. So the goal of this talk is going to be to build meaningful crypto systems. And of course, cryptography has existed for decades, millennia. There have been ad hoc, insecure designs followed by a more principled approach where modern cryptographers began to rely on the hardness of very specific mathematical problems like the RSA, Diffie-Hellman, learning with errors problems, and started to build crypto out of them. And even more recently, we've begun to club many of these problems into generic assumptions, which can be instantiated from a variety of very specific mathematical problems. One example, in fact, the biggest example of such a generic assumption in classical cryptography is what is called a one-way function. This is a function that's efficiently computable, so easy to compute in the forward direction, hard to compute in the reverse direction. What that means is that in the following experiment, if you sample x uniformly at random from the domain, compute y as a function of x, f of x, and send f of x to some polynomial-sized adversary A, then the probability that the adversary manages to find a pre-image of y is negligible. And you should think of negligible as being exponentially small in general, although what it actually means is smaller than every inverse polynomial. And of course, in this talk, we will care about quantum adversaries, so that's why there's the quantum in the bracket. So that's what a one-way function is. These play a very central role in classical cryptography. In fact, the existence of one-way functions is necessary for almost all classical cryptography. And these are not only essential, they're also useful. For example, these give rise to a variety of interesting cryptographic primitives, most notably symmetric key encryption, digital signatures, pseudo-random generators, and commitments. And yeah, I've emphasized quite a few times already that this is necessary for all of classical cryptography, all interesting classical cryptography to exist. So the question then for all us classical cryptographers, which is what I used to do up until about 5 years ago, is the following: do one-way functions exist? And unfortunately, we don't know. We have a bunch of candidates based on the hardness of problems like factoring. There's these hash function candidates that exist, AES and SHA. There's candidates based on the hardness of lattice problems that are plausibly also post-quantum secure. But these are all candidates. And we've tried to analyze their security, tried really hard to prove that they're secure, but there's a major barrier. The barrier is that if one-way functions exist, then P is not equal to NP. And so you would need to at least prove that P not equal to NP if you were to hope to prove that any of these primitives is a one-way function. That's not a great state of affairs, but we live with where we are. It's actually even true that even if we manage to prove that P not equal to NP, it may still be possible that we still don't know whether one-way functions exist, because there's a gap between P not equal to NP and the existence of one-way functions that we don't know how to bridge yet. But this is a very exciting research program in cryptography. But yeah, this is where we are. And of course, I, as a classical cryptographer, lost many, many hours of sleep thinking about this very question of whether one-way functions exist. Until about 5 years ago at Simons, there was a program on quantum alongside a program on lattices. We're talking to other quantum computer scientists led us to the realization that, for many years, it's been known that quantum key distribution is actually possible without making any unproven assumptions. So this is great. And one can ask the question, what about other cryptographic primitives? So there's a bunch of primitives that we care about besides key distribution, including secure computation, signatures, zero-knowledge proofs. If you don't know what those words mean, don't worry about it. I'll tell you about a few of them very soon. But yeah, so the question is, what do we know about building all of these other cryptographic primitives once we have access to quantum resources? Can this be done without any unproven assumptions, just like the case of QKD, or do we still need assumptions? Before moving on, let me tell you about two primitives that will be the focus of this talk. The first is what is called a commitment scheme. This is like a way of locking a message into a box and transmitting that message over inside the box in such a way that the message is unrecoverable until a later point where the sender decides to send a key, which will help the receiver open the box and read the contents. And the guarantee is that before getting the key, the message remains hidden. After getting the key, the box cannot actually be opened to anything except the underlying message. Of course, we don't want any boxes being sent around. So the point of cryptography is to realize this with simply electronic messages being sent between Alice and Bob. They exchange messages, end up with a transcript. The transcript defines what is called the commitment to Alice's message. And the transcript hides Alice's message from Bob. So this communication keeps the message hidden from the receiver. That's the hiding property. And the binding property is that at a later stage, when Alice decides to decommit to her message, she cannot open the transcript or pretend that the transcript was a commitment to any other message other than the original message that was intended. So that's the binding property. Okay. Why is this useful? Well, among other, this is a really core primitive in cryptography, but quantumly, there's an interesting reason that this is useful, and that's tied to the next primitive that I'll tell you about, which is secure computation. So secure computation, as the name suggests, allows a way to securely compute on joint private data. So in this example, we have Alice and Bob, who have their own private DNA information. They don't want to share this information with each other or with any other third party, and yet they want to be able to compute whether or not they're related to each other. Turns out, cryptography gives a way for them to do exactly that. They can compute a joint function on their private data while hiding all secrets from each other and from the rest of the world. So such that the only bit they learn at the end is whether they're related or not. And this is great. This is really useful and powerful. And not only in a two-party setting, this also makes sense in a multi-party setting where you have data spread across many devices and servers and so on and so forth, and you can have them compute joint functions, train joint models on their sensitive data without revealing anything to each other except the output of the computation. So this is really powerful, and it's the basis for many recent startups, and it's gaining a lot of popularity in industry now. So this is a really important cryptographic primitive, and moreover, it implies many other cryptographic protocols just as a special case. So you all may have heard of zero-knowledge proofs. Those are a special case of secure computation. Blind signatures are a special case of secure computation. It's really a general purpose primitive that encompasses many, many different applications. So given that this is really important, a natural question is, how do we realize secure computation in a quantum setting? And 30 years ago, just like quantum key distribution, it was believed that quantum commitments exist that are secure against computationally unbounded adversaries. And moreover, it was also believed that building on these quantum commitments, quantum MPC exists, secure against unbounded adversaries without making any unproven assumptions. Years later, there was a proof that actually commitments against unbounded adversaries simply cannot exist, even when we have quantum parties sending and receiving the commitment over quantum channels. So this was proven in 2 independent works of Mayers and Low and Chow. And what this says is the assumptions required to realize commitments in secure computation in a quantum world are basically still unknown. Now, what we do know, though, is that with access to quantum resources, commitments actually can be used to build secure computation. And as long as the participants are quantum. This was shown in a bunch of works. And note that this is something that's provably impossible without quantum capabilities. So classically, we actually have proofs that one-way functions cannot be used in a black box way to build secure computation protocols. This follows from this seminal work of Impagliazzo and Rurik. And turns out that barrier does not hold when participants have quantum capabilities. So this makes commitments even more interesting as a building block for secure computation. And what this means is minicrypt in a quantum world actually contains multi-party computation, which is very different from what's true in the classical regime, where we know that it cannot contain multi-party computation. So great. So we know one-way functions and commitments are very powerful once you have access to quantum resources. But now, can quantum cryptography be based on assumptions that are even weaker than the existence of one-way functions? And why do we ask this question? Well, it turns out that William Kretschmer first showed back in 2021 that relative to a quantum oracle, pseudo-random states can exist even if BQP equals QMA. Why this was interesting is because 2 works of Anantkian UN and Morima Yamakawa realized that pseudo-random states can be used to build commitments quantumly. So the construction is somewhat similar to what you would do with a PRG to build a commitment scheme. I'm going to show you the essence of it. So what is a pseudo-random state? It takes a classical string, a classical seed, and outputs a quantum state. And the pseudo-random state generator is expanding, meaning the size of the seed is smaller than the size of the output state, than the number of qubits of the output state. And moreover, the pseudo-random guarantee is that the output state is computationally indistinguishable from a truly random state. This ends up yielding a pair of distributions that are statistically far, but computationally indistinguishable. The first distribution simply outputs a truly random string. The second distribution outputs a pseudo-random state. These 2 distributions are far in trace distance, but cannot be distinguished by any efficient machine without breaking the pseudo-randomness property of the pseudo-random state. And it turns out that this can be converted into a commitment scheme. You can informally think of D0 as being a commitment to 0 and D1 as being a commitment to 1. You purify the whole thing and use it to commit. And turns out you cannot, this satisfies both hiding and binding. Okay, hopefully that makes sense. Now, what this means is that relative to a quantum oracle, commitments can exist even if BQP equals QMA. And moreover, commitments can exist even if P equals NP. This was a more recent work of Kretschmer, Kian Sinha, and Tal. And this time they have a classical oracle relative to which commitments can exist even if P equals NP. In fact, it was conjectured in a subsequent work of Lombardi, Ma, and Wright that relative to a classical oracle, commitments can exist even if every problem that can be classically described can be easily solved. So they give an oracle that's going to solve every classical problem you throw at it, including the halting problem, and they show that one query to this oracle is not going to be able to break a quantum commitment scheme. And they conjecture that this holds for even more queries. So what this says overall is that there's a strong possibility that quantum commitments can be based on assumptions that are mathematically weaker than NP hardness or the existence of one-way functions. And not just commitments, there's been a lot of interest in this area with a lot of recent research describing many different primitives, some of which are here on this slide, many different crypto primitives and their relationships with each other and what they give, like private key quantum money, symmetric key encryption, message authentication codes, and so on. And not just those, there's an explosion of the number of primitives that have been introduced and studied. And while this is great, there are some fundamental questions that we can be asking ourselves about these primitives. The first is there a quantum minimal primitive or some quantum meaningful analog of a one-way function that can be used to build meaningful quantum cryptography? The second, are there concrete mathematical problems that are harder than inverting one-way functions and yet can be used to build quantum cryptosystems? And the third is, what connections does quantum cryptography have with traditional complexity theory? I'm going to be able to give some answers to 1 and 2 here. 3 is more or less an open problem. Okay, so first, and this is driven purely by curiosity, let's just try to understand what quantum one-way assumptions look like. So one meaningful relaxation of a one-way function is what is called a quantum one-way function. This is a quantumly computable function that is hard to invert. So this is exactly like a one-way function, except a quantum computer is computing the function. That's all. Another relaxation is what is called a one-way state. Now, here you weaken a quantum one-way function by replacing its output with a state. So there's 2 algorithms. The first is a key generation algorithm that generates random keys. You can also think of these keys as being uniformly random in some cases. And then there's a state generation algorithm that takes a key and outputs some quantum state. And the hardness lies in inverting the quantum state and finding the pre-image key, or more generally in finding any key such that the state corresponding to that key overlaps with the target state. This is what a one-way state generator is. There are some candidate one-way state generators. And in fact, Kretschmer first, his original separation gave an oracle relative to which one-way state generators exist, but quantum one-way functions do not. Some good candidates for one-way state generators are ensembles of states output by random quantum circuits. So in particular, you take a random quantum circuit of some architecture and have maybe a hidden key inside it, output the state generated by the circuit, and the task is to find the key or find the specific circuit that was run to generate the state. These types of ensembles have been analyzed in some recent works. And these are good candidates for one-way state generators. A specific type of architecture that leads to something called a Hamiltonian phase state has also been studied and has some type of worst case to average case reduction. So these are other good examples of one-way state generators. Now, why should we care about them? Are they useful? Can they be used to build commitments? One barrier that comes up when trying to build commitments from one-way state generators in the same way that you'd build commitments from a one-way function is to try to count the number of pre-images. So when applying classical techniques like Hill, for example, which is the seminal work of Hastad, Impagliazzo, Levin, and Luby that builds PRGs from one-way functions, one key barrier in applying those techniques to the quantum setting and putting a Q in front of those techniques is that you need to count the number of pre-images of any given image and then apply some type of hash function to reduce those pre-images. And problem when dealing with quantum states is, what is a pre-image? So you could have two keys that lead to two quantum states that overlap with each other somewhat. So they're not the same state, they're not orthogonal, they have some non-trivial overlap. And now do you count a preimage of one of the states as a preimage of the other? Or do you not count it? Or is it half a preimage? It's not clear. So this makes things really messy. That's one major barrier that shows up. And in order to overcome this barrier, one idea that's used, and this is in this work with Kabir, is we show that you can take a one-way state generator and generically replace its output states with some classical information that you can then use to build a commitment. And what is this classical information? So what is this classical information? Basically, yeah, approach is going to be to try to convert the quantum state into some classical description while still retaining the hardness of inversion. A natural place to look for is tomography. So you could look at the state, perform quantum state tomography on it, take the output of tomography, the classical output, as a description of this state. And you know that if given the state, the preimage was hard to find, then hopefully, given its classical description, also the preimage is going to be hard to find. So that's the hope here. But this clearly doesn't work because the size of this description of the state is in general going to be exponential. And in general, n-qubit states do not actually have polynomial-sized classical descriptions. And we cannot go into the exponential regime because we want an efficient construction of our crypto primitive. So instead of doing tomography, we use shadow tomography. So Scott talked about this a little bit earlier today. The version we use is from this work of Huang, Kueng, and Friskill, but this notion was introduced by Scott in his 2016 paper. And the idea is the following. You take sufficiently many copies of a quantum state and perform some efficient procedure. We really need this procedure to be efficient. So you perform an efficient procedure on the state to collect some classical information about it. We'll call this classical information the shadows. And then you require that there is an inefficient estimator that given the shadows and some property x estimates the overlap between the state defined by x and the state in question. So the overall requirement, the two overall requirements that we have here are that the shadows you should be able to get them efficiently given the state, and these shadows should be usable. You should be able to use them to estimate exponentially many properties of the state. You should think of these exponentially many properties as being the overlap between the state in question and the exponentially many states that arise from the exponentially many keys of your one-way state generator. Okay, so there's an exponential number of such states, and you want to be able to use the shadows to check the overlap between each of those states and your state in question. Okay, I'll skip the formal requirement here. Hopefully all that made sense. So turns out if you take the output of a one-way state generator and replace the state with its shadows, meaning you build a primitive where on input a key x, the primitive outputs the shadows corresponding to the output of the one-way state generator, then this makes the output classical while still keeping it hard to find the preimage x given the shadows. So you've made the output classical by replacing the output state with its shadows, and the preimage x is still going to be hard to find. And we ended up calling this resulting primitive a one-way puzzle. And we showed that one-way state generators imply one-way puzzles. So what is a one-way puzzle? A one-way puzzle is nothing but a quantum process that samples hard on average problems together with their solutions. So you have an efficient quantum sampler that's going to output pairs of strings x and y that satisfy some relation. So that's what it means by problem and solution pairs, such that given some string y, it's computationally intractable to find an x that satisfies the relation. So this is just nothing but a search problem with an efficient sampler that outputs pairs of strings that satisfy your search problem's relation. An important note here is that this relation is not necessarily an NP relation. This is important because this is going to be useful in the future when we try to build these primitives from beyond NP hardness. And moreover, if the sampler was efficient and it was classical, then it is without loss of generality for this relation to be an NP relation. This is not too hard to see. You can pull out the sampler's randomness, use that to define another relation. It's going to be an NP relation. So the crucial aspect of using a quantum sampler is that you cannot pull out its randomness in this way, and therefore cannot use it to define any efficiently checkable classical or quantum relations. And so really, the fact that this relation is not efficiently computable is going to be important. Okay, so what we showed is that one-way state generators imply one-way puzzles, and that one-way puzzles defined this way imply quantum bit commitments. The second part ends up being fairly non-trivial, but I'm going to hide all of that non-triviality under the rug here because I want to talk about more interesting things. Okay, so we've gone one by one over this task of defining what quantum one-wayness looks like. And bear with me, we're almost at the end, and there's a point to this. It turns out that initially all of this was done out of pure curiosity. So just curiosity-driven questioning, a curiosity-driven line of questions that said, well, in what ways can you relax classical one-way functions to get quantum analogs that are both meaningful and useful and give you something that's cryptographically important? But it turns out that defining relaxations in this way has helped find ways to realize these primitives from natural assumptions that occur in other contexts. And I'm going to get to it very soon. Okay, before we wrap this part up, let me just say a little bit about this last primitive called a state puzzle. So a state puzzle captures the hardness of synthesizing a quantum state given a public string identifier. There's a sampler, again, quantum efficient sampler that outputs a string and a state pair. And now the search hardness lies in searching for the state given the string. So meaning, given the string S that's generated as an output of the sampler, outputting a state that has non-trivial overlap with the corresponding remaining state get psi S is hard. That's the hard problem. And it turns out this hard problem is implied by other interesting quantum crypto primitives like quantum money mini schemes. More generally, quantum money implies this. So this is an interesting primitive to look at as well. And now that we've defined various one-way relaxations of quantum primitives, it turns out these are related to each other in some nice ways. I'm going to spare you all the details, but let me just mention that all of these primitives end up implying one-way puzzles, and one-way puzzles end up implying commitments. So basically, all forms of quantum one-wayness that we've been able to come up with imply one-way puzzles, which in turn imply commitments. Also, there are other works that directly get commitments from some of these primitives without going via the one-way puzzle route. But yeah, I'm going to leave this on here for a second, again, to just emphasize that it seems like if any of these other quantum types of one-wayness exist, then one-way puzzles exist. And if one-way puzzles exist, then commitments in MPC exist. Okay, so we've gone through this exercise of defining quantum relaxations of one-wayness, but I'm going to now try to address the elephant in the room, which is what is the point of all this? It's nice, you can be curious about, what classical reductions can you put a Q in front of and they still work, but why? And one answer I have for you is that after we were able to prove some of these implications actually allowed us to base quantum cryptography on concrete mathematical problems that seem to be much harder than inverting one-way functions. And these are problems that have been studied elsewhere outside of the cryptographic context, seem to arise in nature in other settings, and also seem to have cryptographic implications. And the reason that this was discovered was because of this seemingly futile, curiosity-driven exercise of understanding how these one-way primitives relate to cryptography. Okay, so let me now go on and describe in the second part of this talk how one-way puzzles, which as we saw imply commitments, can be built from mathematical problems that are harder than problems in NP. So our goal now in the second part of the talk is to look for sources of hardness beyond NP. And this is a picture of some complexity classes and their containments. And we see that the polynomial hierarchy contains NP, and P to the sharp P contains all of these classes. So one natural candidate class whose hardness we could use to build quantum cryptography is P to the sharp P. So our goal is going to be to build cryptography, specifically one-way puzzles, from the mildest possible assumption. And we know that one-way puzzles are invertible by sharp P oracles. So they exist only if P to the sharp P is not equal to BQP. This was proven in a work of Cavalier et al. It also goes via this equivalence between post-BQP and PP. And yeah, so it's not very hard to see how to invert one-way puzzles with sharp P oracles. And so at the very least, we need P to the sharp P not equal to BQP if we want one-way puzzles to exist. So that means, can we start with the assumption that P to the sharp P is not equal to BQP and build one-way puzzles from this minimal assumption? That was our dream when we started. Try to prove this. Now, let me tell you what sharp P is. It's a counting complexity class, captures the complexity of answering counting the number of satisfying assignments to a given Boolean formula. And the classic sharp P complete problem is the problem of computing permanence of matrices. The permanent that I've written it out here is just like the determinant, except you have plus signs in between all the terms. And this problem is known to be sharp P hard in the worst case, and also to be sharp P hard in the average case for many natural distributions over matrices. So this is a great problem for building cryptography because we're always looking for average case hard problems. And we need average case hardness at the very least. Great. Why didn't classical cryptographers try this? Because it was hopeless. We need NP hardness. Sharp P is not going to cut it. But with quantum cryptography, it looks like sharp P hardness could cut it. OK, so can we build quantum cryptography from the hardness of computing permanence? This is still a dream, as is, but there's been some progress, and that's what I'm going to tell you about. So a key bottleneck in trying to realize this dream is the following. Recall that in a one-way puzzle, there's an efficient puzzle sampling algorithm that needs to efficiently sample input-output pairs for the puzzle, or puzzle and solution pairs, where now and the hardness is that no quantum polynomial time machine should be able to find x given y. Why is this a bottleneck? Well, we could try setting x to be the hard to compute part, which is the permanent of the matrix, and y to be the matrix itself, and say, maybe this is our puzzle, and this is secure because we know that in the average case, given A, it's hard to compute the permanent of A. The problem is if you read these two lines, there's a contradiction, because that means the first line insists that you need an efficient sampler that's sampling permanent of A along with A. And it seems unlikely that random matrices corresponding to certain natural distributions can be efficiently quantumly sampled together with their permanents. So this process, this efficient quantum process that samples both matrices and their permanents together for you seems hard to realize in general. And so that's the main bottleneck. And we now turn to the literature.
I mean,
Yes.
but it's not completely ruled out because there could be something that samples X and Y together, right?
I think, yes. In fact, eventually we get a one-way puzzle. It's just not as easy as you think. You just
sure.
hold your, no, it's the other way. But yeah,
The contradiction would be if you assume you have to sample Y first and then X conditioned on it.
that is hard. Yes,
Yeah, right,
yes, exactly. Yes, but if you look at natural distributions, this seems hard to do. That's the main thing I want to point out here. Okay, so we turn to the literature on quantum advantage, where all of these beautiful works showed or relied on the following fact, which is that quantum circuits are able to efficiently sample from distributions, sample classical strings from distributions, such that the probabilities of sampling certain strings, or the probability that the circuit samples a given string, encodes the permanent of some related unitary matrix. So if permanents are hard to compute, that means these probabilities assigned by the quantum sampler to various strings in its support are going to be hard to compute. Okay, so have we made our life easier? Maybe we can use the hardness of computing probabilities to build puzzles. Now, so what we have is that for a random string in the support of the distribution, it's hard to compute the probability assigned by the distribution to this string. So maybe we try again the same approach, set our x, the hard to find thing, to be the probability, and y to be our string A. Maybe this works. Maybe this, maybe this is a good puzzle. But turns out this is bad too, for the same reason that the permanent the candidate based directly on permanence was bad. Why? We need to be able to efficiently sample x and y pairs together, which here that means you need to be able to efficiently sample a string together with the probability assigned to the string by this distribution. And this again seems to be quite hard to do. So all that we have that is easy to sample is a random string from the distribution. So A's distributed according to the quantum sampler's output are easy, but computing their probabilities or approximating them or even sampling them together with A in general seems hard. Okay? So it seems like we're back to square one, but it turns out we can use some indirection here. And in particular, Chung, Golden, and Gray introduced this notion of a distributional one-way puzzle, which captures the hardness of distributionally inverting the outputs of efficient samplers. So here you again have an efficient quantum sampler that outputs x and y pairs, such that given y, it's computationally intractable to sample x distributed according to the marginal distribution of the output of the sampler given the string y. So maybe you can think of this as post-selected sampling. So post-selected on some string y, it's hard to reverse sample x distributed according to the output of the sampler. What they showed is if this distributional version of a one-way puzzle exists, then one-way puzzles exist and commitments exist. And they showed that this is actually equivalent to one-way puzzles. Okay. So great. So there is this distributional primitive. Maybe this makes our life easier. It turns out that it does. Consider the following candidate distributional one-way puzzle. The puzzle sampler is going to sample a string from the distribution. Say that the string is n bits long. It's then going to sample a random index from 0 through, I think that should be 1 through n, not 0 through n minus 1. Sorry about that. And then it's going to truncate the string to the first I minus 1 bits, output that as the y, and the next bit as the x of the puzzle. So recall that the hardness in inverting the puzzle lies in sampling x given y. That was the distributional one-way puzzle that we just talked about. And so I'm going to claim that for a sampler defined this way, given the prefix of a string, it's actually hard to sample the next bit. Turns out that if this next bit is actually hard to sample, then we will be able to approximately compute probabilities assigned by the distribution to every string. And that's where the hardness was. Okay, so I'm going to pause here to see if there's any questions. Okay. So let me just remind everyone again. The construction of the puzzle is simply sample a string, truncate it to a random prefix, and output that prefix as the puzzle. And the solution is supposed to be the next bit of the string, sampled according to the right distribution. Now let's try to prove that given an adversary that on input a prefix of such a string samples the next bit perfectly, it's possible to construct a machine R that uses this adversary to approximate our probabilities. In particular, it's going to approximate the probability assigned to every complete string in the support of the distribution. Let's say our string looks like this, 0, 1, 0, 0, 0, blah, blah, blah. We could run our adversary on the empty string many times to approximate the probability assigned by the adversary to the 0 string, to the 0 bit, I guess. Now we run our adversary on prefix 0 many times to approximate the probability that the adversary outputs next bit 1. Multiply these two to get the probability that the distribution outputs any string that begins with 0, 1. Now we know the probability that the distribution outputs any string that begins with 0, 1. We run the adversary on 0, 1 many times to approximate the probability that the next bit is going to be a 0. Multiply and continue this way. Okay? It turns out that this process gives a nice inverse polynomial relative error approximation to the probabilities assigned to various strings in the support of the distribution. Now, I want to point out that even approximating these probabilities in the worst case is known to be sharp p-hard. I also want to point out that we started out by trying to rely on the hardness of computing permanents or computing probabilities, whereas the only thing our reduction has been able to do is approximate permanents. So the hard problem we need is the hardness of approximating permanents or probabilities, and not the hardness of exactly computing them. And this is where I am trying to point out that even approximating these probabilities is sharp p-hard in the worst case. And computing them is sharp p-hard in the average case. But what we need is both average case hardness and hardness of approximation together, which is not known to be sharp p-hard, but is conjectured to be sharp p-hard. Okay? And I'll say more about that in a second. I also hid many, many details under the rug, but let me just summarize what was going on here. If we built a one-way puzzle such that any distributional inverter for the puzzle could be converted into a probability under a quantum polynomial time reduction to a probability approximator that approximates probabilities on average over strings sampled from our efficiently samplable distribution. This requires a fair amount of work. I gave a super oversimplified proof. And the assumption that we end up contradicting with this reduction is the following, that there's a quantumly efficiently samplable distribution A and some polynomial P, such that the probabilities assigned by the distribution to strings in its support are average case hard to approximate up to inverse polynomial times 1 by 2 to the n additive error by quantum polynomial time machines. Okay? So the mathematical problem that we're relying on is the hardness of approximating probabilities assigned by quantum samplers to strings in their support. Now, has this problem been studied before? Turns out yes. The literature in sampling-based quantum advantage actually conjectures that this problem is sharp p-hard. In particular, the place we came across this first was this paper of Scott and Arkhipov on boson sampling, where they showed that permanence where they showed that a certain boson sampling setup demonstrates quantum advantage in that no classical sampler can sample from the same distribution as the output of this quantum sampler. And the assumption they needed was of the following form: permanence of random matrices with Gaussian, of certain random matrices with n01 Gaussian entries are sharp p-hard to approximate on average. It turns out that this conjecture implies the assumption we need. In fact, we need a weaker form of it. Similarly, I'm sure all of you are aware of random circuit sampling. In order to prove that random circuit sampling demonstrates quantum advantage, it was conjectured that output probabilities of random quantum circuits are sharp p-hard to approximate on average. Again, this conjecture implies the assumption we need. You could also look at conjectures that have been made for other circuit architectures like IQP, and those are also good enough for us. So basically, if you assume any of these conjectures, you get that this assumption here, or this problem here, of approximating probabilities is sharp p-hard. So the hard problem, again, is for a quantumly efficiently samplable distribution, approximate the probabilities assigned to strings on average up to this much error. And like I said, it's been conjectured that this hard problem is sharp p-hard. So under those conjectures, and assuming that quantum polynomial time machines cannot solve sharp p-hard problems, you get cryptography. Now, does this hard problem actually imply the existence of one-way functions? Recall that one of our goals as we started this research program was to try to build quantum cryptography from problems that do not imply one-way functions, that are much harder than inverting one-way functions. Now, the quantum advantage literature actually conjectures that this problem should not imply one-way functions. Why do I say that? It turns out that proofs of quantum advantage, or proofs of the fact that classical samplers cannot sample from these same distributions, rely on this probability approximation problem lying outside BPP to the NP. So, on the other hand, if a BPP reduction could use a one-way function inverter to approximate these probabilities, then that would put this problem in BPP to the NP, which would contradict what is needed for quantum advantage. So that means really, at least under BPP reductions, this problem should not imply one-way functions. In fact, we don't even expect BQP reductions or pH reductions to be able to build one-way functions from this problem. Okay. So the main theorem, which I hadn't stated until now, is assume conjectures from the sampling-based quantum advantage literature. And remember the three conjectures I listed, assume any one of them. Then one-way puzzles exist if P to the sharp P is not equal to BQP. So the dream was to get just the second line, but we do it under conjectures. Now, you can ask a few questions here. What if I don't believe the conjectures? Like, what if I don't believe that all of these probability approximation problems that the conjectures talk about are sharp P-hard, but maybe only at the 17th level of the polynomial hierarchy? That would, it would still be good enough for the quantum advantage claims. And turns out that would still be good enough for us. We just have to update this to say that BQP cannot solve the 17th level of the polynomial hierarchy. So this would still give us cryptography from problems that are harder than problems in NP. Another potential question is, can we hope to obtain one-way puzzles without assuming or proving this conjecture at all? Which is, can we hope for this dream to just be provable? One-way puzzles exist if and only if P to the sharp P not equal to BQP. This may be hard. Why we think this may be hard is because if one-way puzzles exist that are not also one-way functions, like if the same primitive, if the same construction of a one-way puzzle is also not a one-way function, then that construction demonstrates quantum advantage. It has to, because if it's not a candidate for quantum advantage, then there is a classical sampler that's going to be able to sample from that distribution, and that's going to give you a one-way function. So in other words, if you have one-way puzzles that are not also one-way functions, then you have some type of quantum advantage. So if you could do this, we think that this is not exactly formal. There are a few caveats here and there, but we think that this more or less would give you quantum advantage, sampling-based quantum advantage without conjectures, or without, from worst-case complexity assumptions. So it seems like this is inherently tied to quantum advantage. This setting of quantum cryptography without one-way functions is inherently tied to the kinds of assumptions you need for quantum advantage. Finally, can other cryptographic primitives or search problems that can be broken by sharp P oracles be used to build one-way puzzles? So again, this is indicating that if P to the sharp P is not equal to BQP, then you have commitments. Does that mean that if you have any cryptographic primitive that a sharp P oracle breaks, then that implies commitments, and then you don't need to assume this? Yes. If you assume the conjectures, then this is just true. So if you assume the conjectures, then any quantum primitive that can be broken by a sharp P oracle, but is secure against BQP machines, is a secure crypto primitive, implies the existence of commitments. So you can get an arrow towards commitments pointing from any quantum crypto primitive that you manage to break with a sharp P oracle, assuming the conjectures. Now, great, but again, are we stuck with the conjectures, or can we get rid of them? It turns out that one-way puzzles are an average case hard primitive. In fact, we show that they're equivalent to the average case hardness of approximating probabilities. Do other average case crypto tasks also imply the average case hardness of computing probabilities? And this turns out to be true for one example that I'm going to talk about next, which is state puzzles. So if you recall, in a state puzzle, you had an efficient quantum sampler that output a string in a quantum state, and the hardness was in synthesizing the state given the string, so in the average case. And what we show is that without making any assumptions or conjectures, state puzzles just unconditionally imply one-way puzzles. In fact, they are equivalent. The other direction is trivial. And what this ends up doing is also giving an amplification theorem for state puzzles, which means, just going back here, if it's hard to find a state that has high overlap with the target state, then that means that there exists an amplified puzzle where it's hard to find a state that has any non-negligible overlap with the target state. So a mild form of hardness of inverting implies a strong form of hardness of inversion here. That's just another consequence of this Sharpie way of thinking about things. I'm sorry, I don't have time to get into the details of this equivalence, but I'm happy to talk about it afterwards. But essentially what we do is say that the hardness of synthesizing a state corresponds to the hardness of approximating probabilities on a given distribution, which I already told you is equivalent to the existence of one-way puzzles. So you can convert the hardness of generating states to the hardness of approximating probabilities and convert from there to one-way puzzles. Okay. I also want to point out that a completely different approach to building commitments from state puzzles was proposed independently by Kian, Reyes, and Sandry. Okay, I just want to say a little bit about the relationship of quantum cryptography with traditional complexity and wrap up. So recall that we started out by saying that in quantum minicrypt, one-way functions exist, and that means multi-party secure computation exists, commitments exist, also signatures and public key encryption with quantum public keys exist. We know all of this to be true, but it turns out that there's a world where we don't need NP to be hard for quantum polynomial machines. We just need P to the sharp P to be hard and make a few conjectures or assume any one of those conjectures that I told you about. And even in this world, commitments and MPC can exist. So you don't need necessarily NP hardness. P to the sharp P hardness can suffice. And of course, again, just like NP not equal to BQP is not the same thing as the existence of a one-way function, P to the sharp P not equal to BQP is not the same thing as the existence of a one-way puzzle. You need this hardness of approximation on average, which is also a feature of which is also a requirement in quantum advantage settings. And there are not just these two worlds. You can also have many intermediate worlds. This is just for your information. There can be other settings where one-way state generators exist, but one-way puzzles do not. Quantumly computable one-way functions exist, but none of these previous primitives exist, and so on. There's been a lot of study of like the strength of these assumptions, and we know now that in increasing order of strength, these different types of quantum one-wayness look like this, and with separations between each of these worlds. So there are oracles relative to which puzzles exist, but one-way state generators do not. State generators exist, but quantum one-way functions do not, and so on. Okay, so let me now wrap that up with some open problems. The first one that I think that I would like to bring to this audience is to try to see if we could prove sharp P-hardness of approximating probabilities, essentially the conjectures from the quantum advantage literature under quantum reductions this time. So in the quantum advantage literature, we really want classical reductions to prove sharp P-hardness. On the other hand, here for cryptography, we're okay with quantum polynomial time reductions. Does that make things easier? I don't know, but that could take us a step closer towards our dream of eliminating the need for conjectures. Can we build one-way puzzles from worst case or average case NP hardness? So forget about sharp P, even though you could say something interesting about sharp P. You still need conjectures. What if we set our sights back on NP? Can we remove the need for conjectures? Or can we use even weaker complexity separations along with whatever conjectures you want, like BQP not equal to P space? Can we use that to build quantum cryptography? Yeah, that's it. Thank you so much.
Okay, we have time for questions. Any questions for Dakshita? Okay, if that's not the case, then let's thank Dakshita again.
Thanks.
And we have half an hour, and then we have a talk by VA.